Hi everyone, are you able to hear me? Great, great. All right. So question from Hank is that is today the last class? No, today is the second last class. Tomorrow is going to be the last class. All right. Okay. So before we start, do you have any questions for me? No questions? Yes, tomorrow we will discuss the project and yeah. Then tomorrow I will discuss the project, assign the project, and then we can, in case you guys want to form the teams, as some of you want to do, let me know. Okay, so we can form the teams accordingly. We can discuss the team formation tomorrow, and then we go ahead. All right. Okay. So all right. So I've started the recording, and today we are going to cover a few topics. And some of those topics are going to be we'll talk about key value RDDs quickly. Then we'll talk about join operations on key value RDD. Then we'll talk about how to save data and read data from a file. Okay. And this one we will basically try to do a proper project rather than talking in air. Okay. We'll do a proper project. All right, and then we'll talk about Spark streaming. So this is what I have in mind to cover today. Okay. Any questions before we start? So Deepak says that today web console is not working. Okay. All right. Just give me a second. I have something urgent to attend to. All right. So Jayaprakash is saying that last week's discussion notes are not loading. Okay. Okay. Sorry about this. Okay. So Deepak, you have e.cloudxlab or f. or g.cloudxlab as console. What is the URL for your console? E. No, E is working. I tested today. So these question is Kafka, MLlib, and GraphXL will be covered today. Kafka will be covered today. MLlib and GraphX we will take a look tomorrow. We'll just go take you through one example each, and that should be good enough. Okay. So Deepak is saying there is an automatic refresh after 5 to 10 seconds. Maybe there's some plugin in your browser which is causing this. Okay. Take a look at that and then we'll talk about it. All right. All right. Great. Any other question you have for me before we jump into today's session? No questions. All right. So, all right. Pankaj's question is, how can we load a JSON file? All right. So, loading JSON file is basically, let me digress a bit, or I'll take it as because I have that in mind today. Okay, I have that in mind, and we can discuss that time. All right. I have that in mind today. All right. So we will do that today. Okay. I'm assuming the recording is going on. Is it? All right. It's going on. All right. So any other questions before we move further? Okay. All right. So so far what we have discussed is a particular kind of RDDs, and we have always assumed that RDD is in the form of an array. Okay. All right. So the way we have looked at RDD is that every object is kind of opaque to us. All right. So opaque to Spark. So so the way Spark has been looking at our data is you have some data, you load it as an array or RDD, and every element contains something. That every element could be number, could be string, could be a complex object like a tuple, or further, the object itself could be an array. Now, so I mean, when you deal with data, when you deal with most of the kind of data, you generally want to have something like a primary key, right? In a table, you have a primary key or a column called ID column. And based on that ID column, you do various operations, keeping the similar kind of philosophy. Okay, keeping the similar kind of philosophy, Spark kind of provides you certain operations where it is assumed that your data contains tuples. Tuples as in data contains row. The way you have table, every row contains many columns. Similarly, the key and value kind of RDDs are nothing but tuple RDDs, in which every object is a tuple. Okay, so I'm using tuple, record, on row interchangeably. Okay, and that's how you should be looking at it. So tuple, record, or a row, all these three data structure or three words, they represent a data structure which contains some values. Okay, so although we call them key value pair RDD, but they in effect are basically tuple RDD, which could contain multiple value. Out of this multiple values, multiple columns, the first one has a special significance. First one is generally considered as a key. Okay. If you want to reform it and you want second one to be considered as a key, then do a map, execute a map function, move the second one to the key. Okay. So there are special operations on RDD which are made up of tuples or key value pairs. All right, these RDD are called pair RDD. Pair RDDs are useful building block in many programs. For example, pair RDDs have reduce by key kind of operation. Okay, they have group by key, reduce by key, order by key, and so on. There are some extra functionalities provided on the pair RDDs. Okay. So the way it's defined in Python, it's a similar way. It's also defined in Scala in this form. It's also called tuple. Tuple is immutable sequence of object. Same is in Scala. You can convert it into a list, convert a list into tuple. That's very much true. All right. Let's take a look at a most simple key value pair RDD. All right. Are you able to see it? Okay. So let's take a look. What is it that we're trying to say? Okay, we are trying to say this. It's nothing but let me also further make it a little more simple. Let's define it separately. I call it input data equals this. You see this? All right. All right. So first I define, okay, let me make it a little smaller so that we all can see it. Okay. So I'm defining this particular variable, you can see. All right. Okay. Then I'm saying parallelize input data, whatever. All right. Then I'm saying now, once we have created this RDD, okay, we can execute function on it. Okay. I'll call it key value RDD, and then, all right. So is this input data RDD right now? Here is input data RDD. Yes or no? Quickly. That's right. This one is an RDD. This is just local variable. This is just local variable. And I'm I'm converting a local variable into an RDD using sc.parallelize, and then I'm executing reduce by key. Yes, it has three tuples, first tuple, second tuple, and third tuple. Okay, and if the way Spark is going to look at it is, this is a key, this is a value, this is a key, this is a value, this is a key, and this is a value. So when we say reduce by key, what does it mean? It means that group this data by the key, and for every group do the reduce. All the values should be reduced. So it is same as map reduce. You remember, in case of map reduce, we used to first create key and value, and then we'll say in the reduce we will automatically get the data grouped by the key. Similarly here, the data has been grouped by the key, and the value is being reduced two at a time, until the two values will be combined together into one, keep until only one value is remaining out of the whole list. Okay, so we are saying reduce by key, and the way you convert two values into one value is by summing them. Okay, yes, the key is A and value. So sorry, no, it's not key and value. Again, sorry to confuse you. No, I'll explain again. This is very good questions, and I'm happy that these questions are coming. Okay, so let me give you this. You might want to try it. Okay, so I hope this up to here everybody is clear, right? Okay, now what happens in case of reduce by key? Reduce by key is equal to saying that first group this data by the key. Okay, when you group this data by the key, what would happen is this will be converted into something like 1, comma 2, comma 3, right? And then 2, comma 4. Okay, when you group the data, this is what's going to happen internally. All right, and then once you group the data and then you say reduce, okay, what's going to happen is your reduce function is going to get executed against this. Right, so Jayaprakash, I'm not sure if I can show you this part. I'm just conceptually I'm trying to explain this. All right, let me draw it and then show it a little bit more. Okay, and let me also try to define, let's say 1, comma 6. All right, let me try to define it. Answer will become 11 here. Okay, good. Let me try to show you what do I mean by this. All right, this is very important because this is a basic example and we must know what's going on here. So this was our simple local array. When we said parallelize, it would create an RDD. Okay, maybe this RDD might have say 2 partitions or 1 partition. Let's say 1 partition for now. Okay, and some of the elements would go in one of the partitions. Okay, some of the elements will go, let's say, in first partition, and some might go in the second one. Good. All right, so if you want to see what's going on here, a easier way to do is, let's say we have, again I'm going to define it. All right, 1, comma 6. Oh, good. And now the moment we say parallelize, it's going to create this RDD. Okay, I said parallelize. Now we have kv.rdd. Now, if you take a look at kv.rdd, there's an easier way to do it. Easier way is we use a function called glom. Okay, glom basically merges all the values of a partition into a new RDD, and okay, not glob, glom. Okay, so r.collect, if you say, you will see the difference. You see the, okay, so here you go. So there is first element, second element, third element, and fourth element. Okay, I think it had only one partitions. So what we, okay. No, it has, a single partition only. Okay, so I think I'll try to do something else. Okay, and let me try to say forcefully say three partitions. Okay, I've said three partitions, and then I'm saying collect. So glom, what it does is all the elements of a particular it doesn't seem to work. All right, I got it. So you can see this one, pay closer attention. So you can see this array is made up of two tuples, this one and this one. Okay, while this and this. So first partition is this, second is this, third is this. Make sense to you? If I make two partitions right now, okay, now you can see this is one array, this is another array, and you can see the partition. Good. All right. So you can here put two partitions. I have forcefully put the two partitions. Sasi's question is, can we chain the functions? Yes, you can chain the functions. Okay, you can actually say sc.parallelize and then you put reduce by key here itself. Okay, so you can do everything in a single line. Okay, like with any programming language. Wonderful questions. Okay, so Jayaprakash, was I able to answer your question? So basically here we have forced it to make two partition, and our partition look like this. All right. Now, the moment we say reduce by key has two phases. First, it will group this data based on the key. By default, whatever you define, this is going to be the key, this is going to be the value, this is the key, this is the value. Okay. Yes, that's correct, Sasi. And all right, now when we say group by, what's going to happen is, okay, what's going to happen is like this, group by. Okay, so in group by, there's going to be shuffling. Internally, there's going to be shuffling, and it will look like this. Okay, it will look like this. These things will be combined together, and I'll try to depict it. Okay, so it's going to get converted like this. Okay, 2, 3, 6. Okay, this becomes first tuple, and then nothing else. Okay, so this is group by key, meaning key is 1, so all the values for 1, 6, 3, and 2 are brought together. For 2, there is only one value, so there is only one. And next is the okay, from here, what's going to happen is that conversion is not possible, Jayaprakash, to show it in the console. Okay. Next is that this 236. Okay. So now we are left with these values. Each of this is going to be reduced. Okay. And how does it happen? So out of 236, the function we have created here is this 236. Let me try to demo it a little nicer way. Okay. So first 2 and 3 will be combined together. Okay. And how is that combination going to happen? Based on this function that you have provided. It's a function which says that take two values as argument and return summation of those two values. Okay, if I have to represent it here, it'll look like this. 2 plus 3 is 5. Okay, it will look like this. So this is the function that's converting two values at a time. Now the same function is going to get applied infinitely until there is only one value left. Now 5 and 6, the same function it's going to apply. All right, it is 11. Okay, question from Pankaj is, does it use different partition for this calculation? It does. It basically tries to create some in memory, some on disk, and this phase is called shuffling phase. Here, a lot of shuffling of data would happen. Okay, so, and in case of 4, there is no need of applying the reduce. This phase is called reduce. 2, 3, 6 are being reduced. All right. A question from Hank is, any reason for to make splitted partitions? So I did not get the question. So partitions are splitted. So by default, we have tried to show that since the data is going to be really, really huge, the data that we process, chances are that the data is located in many machines. Therefore, we here there is no need of partitions because there are only 4 variables for 4 tuples, right? It's very small data and it can very well fit into the memory. So although we don't need to create partitions here, just for the demo purposes, we have enforced the partitioning. Okay, we have told here that we have told here that use 2 partitions. Okay, all right. So okay, yeah. What is the key fact to decide number of partitions? Very good question, Hank. Again, all right. Let me try to answer this question. It's a very good question. Who can help me answer this? That's right, Pankaj. Okay. So yes, I'll try to explain. What is the key fact to decide number of partitions? It's a very important question. Okay, it's a very important question. And so although it's exactly the same reasoning as how do we decide number of mappers in case of MapReduce, right? By default, The number of mappers are decided based on where is your data, right? Similarly, number of partitions are decided based on where is your data. Sometimes what you realize is that although your data is very small, but your computation is really, really heavy. In those cases, you might want to create more partitions. Let's say you have many nodes in the network, okay? And you are doing your data, your input data is not that big. Let's say you're trying to download URLs, okay? List of URL, list of a million URL will hardly be few megabytes. And that's not huge data, okay? But what you want is that let the downloading happen across the cluster. In those cases, you may want to repartition forcefully so that there are hundreds of partitions in your RDD. And when you run your map function, which will download the data, that map function will run parallelly on all the nodes. Okay, do I make sense here, Hank? Okay. All right, let me try again. Okay, so let me try to explain with a better example. Okay, so by default, partitions are decided by the data blocks. Okay, if you are loading from HDFS. All right, okay, it decided by your data basically. Okay. All right, but sometimes let's say your objective is to uh, okay, so let me draw it again. I hope that'll make more sense. Okay, so let's say as we were talking about earlier that every partition, I mean, there'll be one worker per partition. There'll be one worker. Each partition can have many values. Okay, each partition could have many values. I'm just trying to draw brackets. Okay, and they will run on one processor. Okay, it will run as a single process. This whole thing will run as a single process. But in this process, the map function, the mapper function, the function which we execute again and again will execute sequentially on every element. Clear here? So this this work, this work, this work. These are three partitions. They will happen parallelly. Okay. Okay. As an example, let's assume that, I mean, I think this will make more sense. Let's say there are 5 partitions having 10 elements each. Okay. If processing one element takes 1 second in a map, how much time the okay how much time the RDD dot map would take. Okay, actually it has to be how much time would the RDD dot map take. Yes, who can answer this? There are 5 partitions and every element takes 1 second. Okay, 10 seconds, right? So more the partitions, faster it is. In case we create now, let's say we have 10 partitions. Now, how many elements will be there in each partition? Quickly. If we repartition this RDD and say that I mean the RDD dot repartition and provide the 10 as partition, then there will be five elements each, because there are 50 elements in total. If you create 5 partition, 10, each one is going to have 10. Okay, now how much time? Here, correct. RDD.map would take 5 seconds. Wonderful. Thank you all. RDD.map would take 5 seconds, but I mean, RDD.map actually is a transformation, so it won't take now, but when we say take or when we execute any action, then RDD.map will take certain amount of time, and that is 5 seconds now. Now, so as we have increased the number of partition, the time taken by while processing each element, but while processing the whole RDD has gone down. But the involvement of the bigger cluster has taken place. Okay, involvement of more nodes has taken place. Does it make sense, Hank? Now, question is, can we keep on increasing number of partition? Answer is no. When you repartition, there is a fixed amount of time that goes in shuffling the elements. Okay, if that time is too much, then it doesn't make sense to do repartition. All right, so this is how you generally take a look at the number of partition that you're creating. Okay, everybody clear with this? This is a very important, I think this is a very important discussion, because understanding of a partition in RDD is actually happening now. Okay, so Hank's question is, number of partition equals to number of node? Not really. If a node has 4 core or 4 processors, it's good. If a particular computer, if particular node has 4 cores, there could be 4 partition on a single machine. Okay, is based on how many workers can execute in parallel. Jayaprakash's question is, on what basis number of partitions will be done by default by Spark? So there are different logics. First logic is based on, let's say you're loading data from HDFS. So in those cases, the number of partitions would be based on number of input splits. Okay, while in case of, let's say, in-memory data, if you're there is certain kind of limit over there, that limit I'm not sure. Okay, so in case your in-memory data is smaller, it won't create much of a partition, but after I mean there is certain limit, I don't know how much is that. After that limit, it would create the partition. Okay, Sashi's question is, what are the partitions in the following scenario? If data we handle is more and logic is less, more logic, less data, more logic. Okay, let me try to take all the 3 cases. It's a very good exercise what we are doing right now. Okay. All right. This is, I think we need to understand, because you may not program later on, but this knowledge will come very handy. Okay. Okay. So, all right. It's a very good point. Now back to the question. If you have more, okay, data is more and logic is less. Okay. Leave it to Spark. Okay, don't enforce partitions, because here, even though the logic is less, if you try to bring the whole data to a single computer, it would be very ineffective. Okay, because it is very tempting to say that, okay, we only need one partition if there is not much logic, because one computer can handle everything. No, most of the work goes in transporting data, and therefore reading data from the disk and transporting data over the network. There will be two things involved. When you say repartition, there will be two things involved: reading the data from the disk and moving it across the network. Therefore, if data is more, leave it to the judgment of Yarn and Spark together to create number of partition by default, because by default they all try to optimize the data locality. All right, now the second scenario is more logic, less data. In those cases, count number of free processors, okay, available number of processors. Okay, if your whole cluster has four, let's say, quad core computers, okay, quad core computers, and there are 30 nodes. So okay, so you are free to keep 120 partitions. All right, now next question is more data, more logic. Okay, more data, more logic. This is a very tricky one. Okay, in these cases, what you have to do, let's say you have humongous data. Let's take a case. Let's take a case of 10 gigabyte. Okay, and you are trying to do a high-end processing. Let me take a very good example of high-end processing: creating a hierarchy. Okay, okay, high-end processing is, let's say, some machine learning exercise, okay, some classification. So let's say you have the data about a 10 gigabyte of emails across the cluster, okay, and what you want to do is you want to classify those emails into spam and not spam. So in those cases, you might have to go through same email, compare that same email with all other emails, or okay, so when you have to classify emails which is of 10 gigabyte, and you have to learn from it, try to approximate which emails are similar in nature, and so on. In those cases, you might have to do a lot of comparisons, right? Lot of comparisons, and therefore, in such kind of scenarios, what you do is you do multi-steps. During processing, you do the repartitioning. You break down your logic such that the logic which applies on the data that remains together, that logic is together. Okay, let's say your logic essentially okay, so the way you structure your logic is that all the data which is closer together, and that particular logic which is processing that data together should be together. Okay, so that the data repartitioning, relocation is minimalized. Okay, and there'll be caching involved, there will be many things involved in this case. Okay, so one is process a little, okay, then repartition or shuffle as in sort, okay, etc. And then you might want to cache the data in between, the data that's going to be used again and again, and so on. All right, so this is This is basically very much subjective. There is no straight answer. You will have to research. You will have to understand what kind of problem are you solving, and according to your problem, whether, let's say, you're trying to order the data based on certain things, you are trying to iterate over the data, and so on. Based on your need, you will have to do all these kind of jugglings, repartitioning, caching, whether running the mapper or running the reducer, grouping, and so on. Or maybe you might have to you know, merge the partition, do the filtering, and so on. Okay, so it will all depend in the third case. All right, do I make sense to you, Sashi, and everybody else? All right, so yes, so this is the reason why we are having this session, so that you understand the different kind of scenarios, and then try to figure out what is to be optimized. Okay, when to call caching. All right, let's say there is certain data which is going to be used again and again. A particular RDD is going to be joined again and again with other RDDs, or union again and again with other RDDs. Then you cache that RDD. Okay, all right. So Maggie's question is, so when we set the architecture of HDFS, what are the best criteria if we are not sure of the type of processing that will be doing yet? So you don't have to worry about that. You can't do much in case of HDFS because you don't know what's going to happen in future. All right. What you can do instead is, it's a very good question. And all right. So I think I will explain today this with a proper example. Okay. So question is, if we don't know in what way are we going to process in future, okay, do we have to make certain choices at HDFS level? Answer is no. Answer is no. Okay. At the HDFS level, you think about this way. If your data is very important and your hard disks are very unreliable, then or your network is very unreliable, you use high replication factor. If your data is not that important and your hard disk, your network is very reliable, and machines are very reliable. For example, you're using SSD and all of your machines are in the same network. In those cases, you might want to reduce the number of replication factor to 2. So those kind of smaller decision you might have to take. Okay. Second is, if your data is going to be used very infrequently, you might want to compress it. Okay. One is number of replication factor. Second is compress it or not compress it. All right. Third is append or create a new file. Okay, that's another decision. So whenever you're uploading data, should you create a new file or you should just append to the existing one? Those kind of calls you have to take at the HDFS level and nothing else. All right. But when it comes to processing, you might want to keep on processing data and cleaning it up and keeping it separate. In case, let's say I was earlier churning the logs of Apache. So what we were doing is, since Apache logs are very huge, we were keeping the logs in compressed format. And and when we transform that format to some meaningful one, we would clean it and keep that data intact somewhere else. So there'll be duplicacy of data in HDFS. That was perfectly fine, specifically because the processing cost is higher and time consumed in processing might be higher. Okay, so those are the kind of decisions you take at the HDFS level. Did they make sense, Maggie? Okay, now, so everybody is able to run this example. Yes, who all have been able to run this? Wonderful. All right. Okay. Now I would like to take you through the word count. Okay. Word count is, the word count is, instead of that, we are taking top 10 most, okay, not top 10, sorry. It's proper word count. Here we are just taking it for example sake. All right. Here I would like to focus on key value RDD. Okay. Who can tell me which one is key value RDD? Lines, words, pairs, counts. Which one is key value RDD? Okay. Is the output of reduce by key value RDD? Output of reduce by key. You remember our discussion earlier when we say reduce by key? We get key and summation of all the values. So when we say reduce by key, we are essentially saying group based on the key and apply this particular function on this array of values for that particular key and do it for all the keys. Therefore, you get key and the value. Okay, it's like saying selects ID comma count star, okay, from pairs grouped by a particular thing. Okay, this is equivalent of saying this. I'll show you. Select a comma some, okay, so I'll just put $0 because we don't have the name for it. $1, okay, group, okay, from pairs group by $0. This is how I would write this in SQL. Does it make sense? Therefore, the result is going to contain two values at a time. Therefore, counts is going to be the word, comma, number of times that particular word has occurred. Okay, so who all wants to do it? I'm going to copy the script again. So can you want to run it again? All right. So I have been able to successfully run it. Anybody wants to run? Okay, so we loaded the text. We broke in the every line by splitting by space, and then once we get the words, the RDD made up of words, we convert that RDD into pair. You see, for one argument which we are getting, we are returning a tuple containing two things. Okay, one actual word, comma, one actual word converted into lowercase. All right, for every word in this big array called RDD, we are converting into lowercase and comma one and creating a tuple. And that's what we are doing it for all the words and creating new one. Okay. To check what's happening at every level, you can say pairs.take 10 or so. Okay. Once we are done with creating pairs, then we are saying reduce by key, meaning for each word group, bring all the ones together, and then sum it up. Okay, sum up all the ones. That will be easiest way to do the counting. And once we are done with that, we are basically printing 10 here, and then saving the entire result into HDFS. Good. All right. Does this script run? Has anybody tested it? Okay, wonderful. Everybody clear about the word count example? Hank, Rebecca, Dheer, Kamal, Venkat, Bernidhan, Michelle, Babu, Shashi, Maggie, Madhu, Christine, Leeladhar, Dabral, Deepak, Pankaj, Babu, and Jayaprakash, Harshvardhan. Okay, extremely sorry what went wrong. Wonderful. So this is one example of operating on key value RDD or pair RDD. Okay, there are quite a few functions available on pair RDD. Okay, such as you have okay, so there are quite a few functions. You can take a look at the manual as well. All right, so here we go. So if you have to just pick up the keys from all the RDDs, create a new RDD of only the keys, you can simply say keys. Okay, simply say keys, and you will only get the keys. Okay, this question is, if we have a text file or log file, how can we decide key value pair? Okay, the way we just now did out of a text file, because we basically created each word as the key and numeric 1 as the value. Why? Because we wanted to group the data or reduce the data by the key. Okay, so based on what basis? Based on the things on which you have to group by, order by, or join by, you make that particular field as the key. All right. So to access keys, you can simply say dot key on keys on any key value pair RDD or pair RDD, and then you will get the results. Similarly, if you want only the values, you can say dot values and you will get the results. All right. You can execute map values, as in run a map function against only the values. If you can say flat map values. Okay. All right. Hank, let me try to execute what I was trying to do. Okay, here we go. So I've created a pair RDD, then I'm going back and count as well. No. So, all right. What does it say? In my case, it would say that the particular file already exists. So I'll just put 1, and let it finish. So it has kind of worked, and you can take a look at D in the HDFS, okay, whether this folder has been created or not. Okay, so I'm trying to show the output of my word count example, and let me order this data based on the date. You see, here it is. Okay, you see, Hank, is it the same as yours? You can see there were only two partitions here. All right, check in the hue and then validate. Right, my home directory is most likely the public. You can see trw and read, everybody can read, so you can actually come to my home directory and read, okay, and compare the results. All right, okay, so you can access the keys, you can access the value, you can run a map function only on the values. Okay, let's say you want to add only something to only the values, then you can run map values. Okay, and if you want to just run flat map on the values, you can do that, and you can do reduce by key as I've shown you. And with reduce by key, you can pass the functions on the basis of which the reduction will happen. Okay, so this is what we were trying to do while we were trying to do the word count. Okay, now the all right, so we have already talked about the word count example. All right, so you can do group by key as well. In that case, it will generate the complex object, but I would suggest not to use group by key, because group by key, all the values for the key will be brought together without reducing. Therefore, the whole object will be in a single partition that might overflow a single node if there are too many values for a key. All right. Similarly, we have set-based operation like map values, in which you can just translate map. Okay, all right. So these are some more operations like reduce. We have already talked about sort by key. So you can order the data based on the key. All right, you can order the data based on the key. All right. Now, there are quite a few transformations available on the pair RDD for various kinds of work. For example, you want to subtract a set from another. Okay, let's imagine that you have one RDD like this and other RDD like this. You can remove all those all those mm, all those tuples which have the same key as the second one. So we can remove A and C from this, which means only B will be left. Okay, so these set-based operations like subtract by, the way we have subtract based on every value, similarly we have subtract based on only the key. All right, then we have join. If you want to join the two RDDs, you can simply join in this way. Okay, this is joining. You can do left outer join, you can do right outer join, and so on. All right, so there are many more functions that we can cover in this class available including co-group. You remember co-group from pig? That's actually all right. Then you can say count by key, and basically counting number of elements for every key. This is even better. In case of our example, what we did earlier, we could actually do count by key. Okay, here in case of word count, we could actually do count by key. All right. So rather than this way, we could say count by key. All right. The only downside of count by key is the counts variable is now local. It's not on the cluster. All right. It is no longer RDD. The output of count by key is local. It's an action. All right. Sometimes you may want to convert it into map that you can do. All right. And it also provides you the lookup key where you want to look up a particular value. Okay. So look up the, right? You can see the has occurred so many times, right? So you can look up a particular key in the RDD. All right. A better idea is that you sort the data and you cache it and then do the lookups. If you try to do lookup again and again, it's going to uh, call the whole process again. Therefore, the data on which you are looking up, first sort it and also try to cache it so that the looking up becomes faster. Also, when you sort it, the data gets sorted and the lookup becomes little binary, and it doesn't have to go into the another partition. Hank's question is, which one you prefer these maps? Word count slash shuffle and reduce. Okay. In between Hadoop and Scala Spark. I prefer the Spark one. Okay. Although both have a similar kind of performance, but doing those same operation in Spark is far better, far easier actually. Okay. All right. Here is a nice project. I would like all of you to pay attention. This is something which can answer you a lot of questions. Okay. So let me first show you the data. You remember our data from yesterday? Okay. So in this folder, data, Spark, project, access in HDFS, you have access logs. All right. Okay. So what is an access log? Access log is nothing but the number of times, it's the log, it's the, how should I say, it's the ledger which records how many requests, what all requests came to the server. Okay. And it's quite useful. It's quite useful. And the project around Spark will be in this. Okay. Project around Spark will be in the in around this particular folder. So in this you can see that there are some requests which do not have an IP address. Maybe they were called internal using an internal connection. Okay. And but other requests are having the IP address of the caller. So this particular IP address is accessing our server. Okay, this IP address is accessing our server. All right, here it shows that the person who accessed our website actually looked at about us page. Shashi is saying you use Pivik for data analytics. Yes, we did use Pivik for data analytics earlier, but right now we are mostly dependent on the Google Analytics and few more. Okay, here it's showing that the person who came to our website was having this particular browser. So we can do a lot of things, lot of analysis on our website. These are real data, by the way. It's a real data from our website. Do not share it with anybody because I don't want to expose it to any of the people who are our competitor or some third party who could exploit this data for various means. Okay, so keep it to yourself, this particular piece of data. Now, here what you see is it's basically the browser. This is the browser. This is the URL which user opened, and this is the request that came. The URL, the whole detailed. Okay, so this is I mean this is basically the actual URL which internally got redirected. Okay. Similarly, if you keep going further, you will see more and more details. Okay. Now coming back to it. Okay. Now let's say you want to clean up the data. Okay. All you want to do is count the IP address. Which IP address are top 10 IP addresses who top 10 frequent top most frequent IP addresses. 10 most frequent IP addresses. That's what we are trying to do in this exercise. Okay. So these are find top 10 IP addresses using this. Okay. So help me out. What are the things you are going to do? Who will help me out? Okay. So this is my data, and this data is there in this folder. There are many files. I want to do it over all the files. Okay. You see, there are 2 pages. There are total 51 files. I want to find out the top 10 IP addresses. Anybody? So what are the things we are going to do? Number one, load the data, right? Load the data. Then remove the records which filter, okay? Filter the data which contain IP. Okay. Third, yes, Kamal is right. Then third, parse every line such that, okay, parse every line and only keep IP address. Okay. Then fourth is first is load the data, filter the data which contain IP address, parse every line and only keep an IP address, and then do the word count. Okay, and take top 10 from sorted word count, and then sort based on the counts and so on. Yes, that's correct, Maggie. All right, so let me try to do that stepwise. Okay, you have to quickly tell me if this is wrong. All right, so this one is the step where we are loading the data. Okay, this is load the data. This is load the data. Okay, and keep only the lines which have IP. Okay, then extract only IP and then count. Okay, let me convert it into 2 slides so that it's not overcrowded. All right. Okay. Is it clear to everyone? Uh, All right. The first line, I'm hoping the load the data is clear to everyone. Feel free to, ask me if that's not clear. So we are saying we are providing a folder name. If you provide only the folder name, it'll pick up all the files from that particular folder. And also this text file, interestingly, unzips the data. It extracts the data. Okay. It uncompresses the data. Okay. And this we are doing just to test whether we have loaded the data correctly or not. Let's take a look at it. You can see it has picked the records. If we say 100, you'll see a lot of lines. Okay, how come it did not? Okay, yeah, maybe this particular, yes. Yes, Kamal. Okay, so I hope this is clear. Next is keep only the lines which contain IP address. How do you do that? Using filter. I have defined here contains IP function. Okay, what is that? It basically checks if a line matches the regex. Let me explain this regex a little bit. Okay, who can explain the regex? Okay, it means, let me go from left. Beginning of the line, okay, beginning of the line, then bracket as in everything within the bracket is one variable. Then we are saying this. It means 0 to 9 or dot, any number of those. Plus means any number of 0 to 9 and dot. This character range, which is there in the square bracket, any number of times, that one, at least once, should be there, then followed by a space, and then dot star, meaning anything, and till the end of the line. Okay, we don't care about anything other than this. We only care about this part. That's why we have put it in the brackets. Okay, because we are going to capture it later on. Okay, digits and dots. Is everybody okay? Is this good format to have? Not really. Had the new scheme of IP address be there, it will fail. Okay, for time being, we are assuming that we are using IP address versioning 4.0. Okay, not the newest one. All right. Okay, so let me show you. So let me take, let's say 10. So it has left only those records which contain IP address in the beginning. Okay. All right. Next is that we are saying, next what we are trying to say is, okay, use this pattern, okay, use this pattern to capture IP address. Okay, this is what we are trying to say here. And then return only the IP address. And once you're done, we are executing map. So every line is getting passed through this function, and this function is returning the IP address. Let's test this function. Okay. Okay. So this basically returns only the IP address found in the beginning of the file. Okay. So if you take a look at IPS, you have only the IP address, and that too we have created a tuple here. Okay. All right. The next is the counts. Okay. We are saying reduce by key, same as word count. Okay, meaning how many times each IP address has occurred. Okay, that's what we are trying to do. So you can see IP address dot take 10. Okay, it's going to take time because it is basically doing a lot of processing. All right. All right. So I think it is stuck somewhere. That's correct. That's correct, Michelle. What's wrong with it? I have pressed Control C. Maybe it got stuck somewhere. IPS dot take 10. Now you can see it has clearly counted the IP addresses. Sorry. Now let me try to do IP counts. Okay, so if I say IP.cache at this point, it'll be a little faster, but let's not bother about it. Okay, let's see if it works this time. Yes, looks like it's working this time. Earlier, I think my network got disconnected. Now you can see that it's trying to basically part by part access the HDFS file. You see? This is the input is split representing the location of a particular file. All right. This is task number 19. And also, I forgot to show you, you can actually open this in a UI. Where did it go? Scroll up, scroll up, scroll up, scroll up. Okay, this is where we started. Now, not this one. Yes. Okay, so we are all right. Okay, so here we are. So you can see that one more thing that every time we run Spark, you get a Spark UI. This Spark UI is quite important, specifically for optimization purposes. Okay, so since my console is at E, so I can say e.cloudxlab and then the port number. Okay, so you can see that These are the take that have executed so far, and the recent one has 52 tasks. Okay, you can see recent one had 52 tasks. All right. Why 52? Because we have 52 files here. Okay, we have 51 file, and I think one action was for take. Therefore, there are total 52 tasks. Okay, so you can see total maps executed how many? 51. Why? Because there were 51 files, and each file is lesser than a block. Therefore, there is no partition of the individual file. There is a single block. Okay. So you can take a look at, you first note down the IP address, sorry, the port number here. Started Spark UI at this particular port, and then open this. This is a private IP address. You will have to translate it into e.cloudxlab, f. or g. Whatever is your console. All right. Is everybody with me? No? Okay. Now, the next step is, let's order this by second column. Somebody was asking me this. Let's say we want to order this by counts, by the value, not the key. Okay. Right now, we have key as the IP address and the value as counts. Now, since we want most frequent IP address, we would like to order it by second column. And how do you order it by second column? Using the sort command. We are saying sort these IP counts by this, using this function. We are saying for each tuple, consider second element to be the key for ordering the data. Okay. And false means we want it descending, not ascending. By default, it generates increasing order, but we want it to be decreasing order. Therefore, we have put false. Okay. And then we say that we access 10 records. Now you can see this particular IP address has accessed our servers so many times. Do you find that strange? Somebody has done, you see, over a period of some time, it has accessed it so many times. You see, 6.4 million times. All right. Possibly DDoS attack. All right. DDoS means denial of service, distributed denial of service attack. Okay, great. So we were able to do a simple analytics using Spark, and there'll be a lot more exercises which are part of the project after this session, which can be done in the similar way. Okay, so who wants the complete script? I am pasting it again by modifying hash to /. You can try it out. All right. So there are quite a few files, and it's a real data. Okay. So I think whatever we had discussed earlier, Hank, so lay out the data to minimize the transfer, as we have discussed this already. It's not helpful if you need to scan the data only once. There's no need of partitioning if you are going to use the data only once. Helpful when data is reused multiple times, specifically in key-oriented operation. And it's available for key value RDD. So you can actually order the data based on the key, partition, cache, and all that. Okay. Spark does not give you explicit control over which key will go to which node. It does not, neither does MapReduce do, because if it gives you that kind of control, it will lose. I mean, it wouldn't work out because every node can be removed or added. All right. And okay, so you can basically bring the data. If you order the data, you will bring the data together based on the key, and that can be used. Okay, that can be basically, you have to ensure partitioning such that the data you want to process together is together. All right. So okay, so there is one example. So here is one case. Let's say you are joining two data sets. Okay, and in that cases, if you see, if the key on which you are joining the data, if it's not ordered, if the actual data is not ordered by the key on which you are joining the data set again and again, it will be very inefficient. Therefore, it makes sense to bring the data together and cache it. Okay, question from Jayaprakash: is composite key possible? Yes. When you are saying sort by, return a tuple containing all the keys on which you want to order the data. All right. Okay. So if you see, if you basically repartition data, then you, or sort the data by the same key, then you generally have the similar kind of network, and joining it becomes very easy. All right. All right. I wanted to show you a few things. Yeah. That's good. This diagram is good enough. So you should order the data in the way when you are joining two data sets, you must make sure that the data is reordered and partitioned. All right. There are quite a few operations that are possible. You should, okay. Any operation that involves shuffling is impacted by the partitioner. Okay. So also here you can see that you can repartition data based on a key or based on a particular criteria or a function. Like here we are saying repartition the data based on the URL, okay, hash of the domain, so that all the data corresponding to a particular domain will go in a single partition. This function is very similar to the partitioner we had at MapReduce. Okay, so this is little too advanced, so I will skip this. So that's pretty much I wanted to discuss as part of key value RDD. All right. Okay, so let's take a break for 10 minutes. Okay. Back by 9:48 p.m. IST. All right. Hi everyone, I'm back. Can we start now? All right. So there was a question from, let me take a look at, there was a question. I think I missed a question. Yeah. Question was from Maggie. Is there a nice GUI for Spark or is it CLI only? Okay. So these days what people do is they generally use notebooks. Okay. So what we have done at CloudX Lab is we have made notebook frameworks available for our students. Okay. So if you go to blog, all right, and there, here we have, okay. So this is the notebook framework, as in you can basically start the notebook and write your Spark or Python code and get started there. Okay. Also, you should keep an eye on CloudX Lab blog, or you can maybe sign up. I mean, become a follower at Twitter. There, you will keep on getting the latest updates about CloudX Lab. Okay, because we are trying to do a couple of things, and we are trying to work on various kinds of projects. All right. So, all right. So let's start. So far we have either converted in-memory data into an RDD or used an HDFS file, correct? So Spark supports wide variety of data sets. You can access data through, it basically can access data through input formats and output formats. And basically it uses the standard interfaces provided by the traditional Hadoop. Okay. And this input format is quite popular, quite powerful, because it's not only Hadoop that uses it. It is used by other systems as well. Okay. So Spark makes it possible to read from S3, HDFS, Cassandra, HBase, etc. All right. And so though, so basically when we talk about data sources or data, there could be four different things. First, data could be in a particular format, whether text, JSON, sequence file, or protocol buffers. Okay. Then format could be compressed or non-compressed, right? Next is where is the data located? Whether it's located in local machine, network file system, or Hadoop distributed file system, Amazon S3. So data could be anywhere. So Spark lets you read the data from all these file systems in all these formats and having different kind of compressions. Okay. So it provides you structured, I mean, the sometimes we will talk about Spark SQL tomorrow. Okay, so it provides you an efficient API for structured data source, including JSON and Apache Hive. All right, and it has built-in third-party libraries. Okay, it actually lets you read. Somebody was asking about the databases. So yes, Spark lets you read from any database, any relational database. Okay, all right. So a normal text file we have already used. from the HDFS. There is nothing much to talk about it here. Okay. And sometimes, let's say there are many files in a folder, and what you want is every file should be loaded as a whole inside an element in RDD. Let's say there are 10,000 smaller files in a folder. You may want to load each file in an element. For example, here, when we say sc.whole text file, what it does is it basically loads the entire directory in a single RDD where every element contains key and value. Key is the file name and the value is the content of the file. Okay, value is the content of the file. And here we are saying map values, meaning execute this function on only the value. Key will remain unchanged in the new RDD. Okay, so here we are saying that for every file, compute the size of the file and print it. Okay, so that's why every file size is being printed here. Okay, so other than text file, other than text file, you could use whole text file, and similarly to save the RDD as such that every individual element becomes a file, you could use save as whole text files. All right. Okay. Another thing is that a frequent question is how to load CSV or TSV. Okay. How to load CSV or TSV. So quick answer is use sc.text file. Okay, use sc.text file. So what would happen is, let's say there is A, B, C. Okay, let's imagine that what is CSV file, comma separated values. Okay, let's say you have a file which looks like this. Okay, which has A1, B1 and C1. This is how, let's say, your data looks like. This is your CSV file. Okay, when we say sc.text file, okay, is going to prepare an RDD which will look like this: A, B, C. Okay, every element is a string A, comma B, comma C, and then let me just remove these round brackets so to avoid confusion. A1, B1, and C1. Now, if we have to break it down, or if we have to parse individual line, right? sc.text file, what it does is it loads the data. Every record is a line, correct? So, so if you have to break it down, if you have to parse it, convert it into tuple, then you might have to basically split, or you can say, okay, sc.parallelize or sc.text file. I think I'll be having some data on which I can show you in practical rather than talking in air. Okay, so do we have CSV file here? I think I'll have a little bit above. In the other folder here. This folder contains the data in the CSV format. Let's say this data we need in our Spark. Let us say we want to compute the number. So okay, a little bit more about dataset. This dataset contains movie length dataset, and what does it have? It has, first column is movie ID, second column is the user ID. Sorry, first column is the user ID, second column is the movie ID, Third column is the rating provided by each individual user. Okay. Also, take a look at the other files. Okay. Let's take a look at the other files. Here, there's something called movies.dat. Movies.dat. What does it have? It has the name of the movie and so on. Okay. So now, provided all the knowledge which we have gained so far, the join commands and all, what we can do is we can load ratings.csv. After uh, loading it, we can load movies.dat and then join the data and clearly see what kind of which movie is what. Okay. Similarly, we can join with users.dat. Let's focus on loading CSV file. Okay. So who can help me with this? So this is our data. This is our data. Okay. So what is it that we want to achieve in this? We want to compute number of movies rated by each person. Okay. It contains, first column is person, movie ID, and rating. Okay. So who can help me with this? All we want to do is compute number of movies rated by each person. Okay. Can we use sc.text file? Okay. So we'll say where input data equals sc.text file. Good. Then once we have loaded this data, then we say we'll say map so that we can split each records. Okay. We'll say split based on comma. All right. So that's, let's say, J. All right. Let's take a look at this if it works. J dot take 10. You see, it has broken each individual one. Now, what we can do is, all right. Okay. So just a second. Let me see what is going on here. Where, okay, res 4 0. Okay, good. All right. Now what we want to do is we want to reduce this data, reduce this. Okay. And all right. Or maybe what we can do here is just after splitting it, we could say pick up only, all right, let me just keep it that way. K equals to J dot map, and we'll say whatever value we have. Okay, whatever value we have, we are going to return V, the first column, and V, the second column. Okay, good. So this K contains actually the only two columns. Rating, it doesn't contain the ratings. All right. Now we can say per user movies equals, we can say K dot reduce by key. Okay. And again, we can do the same thing what we had done earlier. We could say A comma B and A plus B. Okay. All right, let's see if it works, or have we messed up somewhere? Yes, so it has. Oh, wow, this is not really summation. It's basically, okay. I think instead of doing this, what we could have done is we could have just returned one. We could have just returned one. Yes, now it should make sense. Because we want to just count. We don't want to do anything else, right? Now it makes sense. This user has rated 58 movies. This user has rated this much. All right. In the similar way, you can try to figure out the average rating of each movie. Okay, by reduce by the second column. All right. Makes sense to you? So we did a CSV parsing. So here we did a very rudimentary CSV parsing. We basically splitted every line with a comma. It's not really great. In case if you really want to do a proper CSV parsing, you should use a library for Scala. Okay, I'll have to find out what is the CSV library from Scala. Okay, so maybe you can use this kind of library. Okay, you could say CSV reader this, not really this. There'll be some way to read the records from input. Okay. I'll have to see. I mean, there'll be definitely a way to parse it using proper one. Okay. So right now we have used a very rudimentary technique by splitting on comma. Okay. Similarly, had this data been in JSON, the mandatory requirement would be let this data be loaded. Let this data be such that every line is a JSON object. The whole file is not a JSON object. Every line is a JSON object. Only then we could load it using text file, and then using a map, we could convert every line into a JSON object. All right. In the same way, similarly, had this data been in tab separated format, we could have loaded in the same way, except for while splitting the records, we would use tab instead of comma. Does it make sense to you? Okay. So this is how you will read it. Okay. So this is mostly Python. Let me talk about channel. So by the way, Spark SQL, which we are going to discuss tomorrow, has an inbuilt functionality of loading JSON. Okay. So Debral's question is, other than count aggregation max min using reduce function, is there any criteria that is used? Can you give example application or applications? Okay. There are quite I mean, there are some more functions which can become the the valid functions for this. Okay, let me try to explain again. So Debral's question is, what else could be used as part of the reduce function. You remember what was reduce function? Okay, let's say A, B, C, and D. Okay, so the same function will be executed first on two element, then these, and then these. Or it could be this way as well. Okay, this and this. Your function should be such that it should not give different results, okay, in these two circumstances. One is this and other was the previous one, where first we did this and so on. The ordering in which we are going to execute a function, if that doesn't happen, if that doesn't give a problem, it should be okay. Now, question is, what are the functions available that qualify this criteria? What are the functions available that qualify this criteria? Okay, so we had talked about min, max, sum. Okay, these are the three things which we have talked. Have you encountered any other? Has anybody else encountered any other example of a valid reduce function other than max, min, and sum? Yes? No. Average is not, because average is not a valid reduce function. Average of average would not lead to the results. Remember our discussion earlier? So average will be a plus b by 2, then plus, and on the other side it'll be like plus c divide by 2. Okay, so it'll look like this. I'll show you. A plus b by 2. Okay, and when we combine that with, let's say, c, it will become, a plus b by 4 plus c by 2. Correct? This plus this divided by 2, which is totally wrong. Do I make sense, Michelle? Okay, because the same function is being applied even on the result. Okay, the output becomes the operand in the next call, right? So not many functions are there which basically qualify this. Okay, let me ask you a little difficult question. Let's say there is a function f which says that sqrt of a into a plus b into b. Okay, what is this? This is called the what do you call this? It's called a distance between 2 points. It's a hypotenuse. It's uh, the the scalar distance between 2 points. It's a scalar distance of the origin. Okay. So my question is, let us say we have to compute our end goal is sqrt of a square plus b square plus c square plus d square. Okay, can we use this function as a reduce function? Dabral, did I make my question clear? Let us say we are trying to compute the square root of sum of squares of all the numbers in RDD. Do you think we can use this function as reduce function? Okay, more specifically, okay, let me just try to quickly write it because it's going to be quite useful. All right, I'm saying parallelize and my list 1, 2, 3, 4, 3. Let me just not order it because, all right, let's say 13. All right, let's say we want to compute that value. Okay, and we want to basically say that can we use this function to, can we use this function, let's say we are defining a function called, uh, I think there is a function called square root import math. Okay, so we have imported math and sqrt is there. Yes, good. So we are saying define our function such that it takes a double and then returns, it takes a double and returns a double. Okay, all right. I hope it's not looking like too much of maths to you. Okay, 3 and 4 should be 5 actually. Let me just test it. Yes. Okay, so you can see that we have created this function. Now question is that if we do this particular part, okay, and we say x dot reduce, and we are passing of one function. Okay, sorry, we have to convert it into a decimal number. Okay, so let me just convert it into a decimal number. All right, now let me just try to reduce it using function. So it has said the result is this much. Do you agree with this? No? So the answer is that this is actually correct. Let me show you this. Okay, this is actually correct. So what will be this value here quickly? It will be square root of C plus D, right? And then when we, and let's call it E equals this. Okay, so it's going to be square root of F into F plus E into E. Okay, and which is equal to square root of A square plus B square plus C square plus D square. Question from Christine is that what would be the real world scenario where we could use this? Okay, one such real world scenario is in the case of loss functions. Okay, specifically if you're going towards machine learning, in those cases you might want to compute this. Let's take a case of standard deviation. Okay, standard deviation. How do we compute a standard deviation? Quickly, what we do is we subtract. Okay, so how do we compute? We first compute the mean, then from every value, okay, subtract mean from every value, and then square it and sum it. So this kind of function could be used there. Okay, we are basically summing up the square roots. All right, so what I'm trying to say is that it's not only min, max, and sum. There are other functions as well, which could be a valid reduce function. Dabral, did I make sense? No? Okay. It looks little maths, but I mean, if you look at it carefully, all we are trying to do is apply a certain function again and again on the values. Okay, again and again. It's like reverse of the chain reaction. You remember chain reaction where one thing becomes multiple? Here, same chain reaction is leading to one element out of multiple values. So it's converting two values into one value. Okay, so it's a diminishing kind of, it's a reverse of chain reaction. All right. So, okay, so was I able to convey the point or no? I don't think I was able to convey the point because, all right. So, all right, we can actually try to compute. There are other ways also. So as a general thumb rule, in case you're confused about this, always break down your problem into max min or summation kind of things. All right. Always break it down to that. That'll make your life easier. All right. So we are talking about square root of sum of squares. We're talking about square root of sum of squares. Okay. Not really, not really. See, if here, if you take a look at it, so there are two numbers, 3 and 5 and 7, right? 3, 4, 5, and 7. 3 and 4. Okay. So we are not going to count them twice. This, then this. Okay. Try doing it and you will get the answer. All right. Okay. So we're basically saying things like this. Okay. 3, 4, and 5, right? So we say 3 square plus 4 square and square root, which is 5. Okay. And we have 5 square plus 5 square. Oh no, actually, yeah, there's something missing. Okay. This is 5 root 2, right? And actually, in whatever way you compute the square root of sum of this, it's going to be the same. Okay. If you see 3 square plus, If you see, it's the same. Okay, which is same as 5 into 1.414. See that? It's the same. Okay. All right. So yes, a question from Christine is that, so is it true to say that any calculation that can be done via partitioning, then final calculation of those results, then the result is same answer as doing a one big calculation is valid? Right. Is valid to use. Yes, that's correct way of saying that if we can reuse the output and keep on doing it again and again, still the answer is correct. That means it's a valid function to be used as reducer. All right, I hope everybody is with me. All right, so we have already talked about sequence file. Sequence file is a popular Hadoop format. It's composed of flat files with key value pairs. It has markers in it so that the file could be loaded easily, and Hadoop can quickly form input formats based on these markers. All right, so that it can detect which portion of the data has to be sent to which input format, and that way it can form the records very easily from the raw data. Okay, so I think Maggie was asking a question related to this, that if you have some data and we don't know how are we going to use it, sometimes it is safe to store it in sequence files. Okay, RC files or sequence files. All right, because sequence files are very easy to load. All right, and Spark provides a special function for loading sequence files. Okay, you could tell about the data types available in every record. Okay, the input data types of the records, the key and the value. The key and the value, you can see the data type of the key and data type the value you provide, and then it loads the data. Okay, as well as you can save any RDD into a file in the formats of sequence files. Okay, so you can take a look. Sometimes you may want to serialize it. It's not much required. Okay, and all right, so this is okay. All right, so there are quite a few file compression formats: gzip, aljado, bzip, zlib, snappy. So you can use all these kind of files in this Spark. You can load the data from any of these formats easily. Okay, and regular gzip compression can be loaded like this. We have already shown you those cases. Okay, and you can load the data from S3. More details are available. You can take a look at this particular use case at our tutorial on how to load data from S3. Okay, HDFS we have been loading so far easily. All right. Okay. All right. So there are some shared variables. One is called accumulator, other is called broadcast. Okay. So when we call a function like map, every node will get the copy of the shared variables which we are using inside map. And the change to this variable will have no communication back. Okay, so there are various kinds of ways of sharing data. One is called accumulator and other is called broadcast. All right, now here's a quick quiz in case you have gone to sleep, so it will help you in wake up. So question is, if an operator is commutative, An operator OP is considered commutative if this or this. Who can tell me quickly? It's a long back. We studied in maybe undergraduate somewhere. So, so you have to match the types A1 or A2, B1 or B2. Yes. All right. So, okay, in case you don't remember, all right, this is what is known as commutative and associative. Commutative means no matter whether you apply A operator B, means A into B is equal to B into A, right? A into B is equal to B into A. All right. So OP is more like a friend function. A is a friend of B, so B is also a friend of A. So that's commutative. So and associative means if no matter where you put the brackets and how you put the brackets, the result is going to be the same, right? So if operator is plus, then this one is a valid one. Okay. Similarly, greater than is also a valid associative function. So plus and star, plus star greater than less than is actually commutative and associative. Okay. So Dabral, you can note it down. Multiply is also a valid reducer. So any function which is commutative and associative is a valid reducer. Okay. All right. So now the main important part. Let us say you are running a particular MapReduce process. Okay. Let's say your process of data mining is going on or data cleaning is going on, and you would like to get the updates frequently. Let's say you want to monitor the progress. You want to monitor the progress of your process continuously. So you would definitely expect that each individual node who is processing each individual partition, they should kind of provide you the update. Okay. And that's what is the that's what is accumulator. Accumulators provide you the progress. Okay. Accumulators are a way of every node to continuously communicate to the launcher, to the driver, the in a way that it doesn't matter which value comes from which node first. The end result should be correct. Okay. So accumulators are variables that are added to through an associative operation. Okay. So this is how you can create your accumulator. Okay. So in Scala, you can see, so you can basically create an accumulator. All right. So that's my accumulator with the initial value. All right. And then every node can basically update. Every node can keep on increasing the value of this. Okay. So inside the map function, so somebody was asking, like, can we note how many times the map function has been called? In those cases, you can use accumulator. You remember, Jayaprakash, your question? Right? So in those cases, you could use accumulator. It's like a counter. That's correct. It's basically for monitoring the progress. So in an accumulator, it's not only that we have to create it, the we have to create it in this particular format. Okay, you can create your own data types. Here it's not allowing me to string one, but we can create our own data types. Anything which basically gives you a kind of append only behavior. Kamal's question is it for debugging purposes? Yes, debugging or showing the progress to your user and so on. All right, so that's an accumulator. All right, and yes. Okay, so how many of you remember our when we were talking about preemptiveness, okay, where one particular slow node's work was being re-executed, right? As we talked about speculative execution in Yarn. You remember speculative execution in Yarn? No? Good, good. So in this speculative execution, what Yarn does is it re-execute things, correct? Which also means that sometimes Spark's map function might get executed on multiple nodes. The same partition could be executed on multiple nodes, right? That means the results of accumulator could be wrong. Is that true? Yes, the same function may run multiple times on the same data, correct? And if the same function is running on the same data multiple times, does it mean that accumulators will give a wrong result? Yes or no? Other than Jayaprakash and Kamal and Deepak? Anybody else? Yes. So the accumulators will give the wrong results. Why? Because of being little greedy. They executed the function at multiple different nodes multiple times, and therefore you will get the wrong results. Okay. So keep that in mind. It's little risky, and okay. So you can create your own custom accumulators. Okay, and we have. So Maggie's question is, can you code in the function ID into accumulator so that it can know? Mm, so basically, these variables are kind of, you know, thread safe kind of variables. You remember if you are sharing a variable inside all the functions and all. Yeah. So yes, so every variable is separate. So there could be multiple variables. So you don't have to track the IDs of every function, every variable. Okay. So the name of the variable itself is an ID. Maybe I understood your question wrong. So I think you're talking about speculative execution, right? And if you try to code the function ID into accumulator, that also means that if the same mapper is executed on multiple places, then the same function ID is going to go there. And there is no unique function ID per se for every execution. Okay, unless there is something called process ID, but that wouldn't mean much. All right. Okay. The other thing is that let's say there is a particular piece of code that you want to send to all the nodes. In those cases, you could use broadcast variable. Okay, you could use broadcast variable. So you could broadcast this particular variable to all the nodes. Okay, this is how it looks like. So basically, you could, while launching a process, you could broadcast a particular variable, and then it will go to all the nodes. It allows program to send a large read-only value to all worker nodes. Okay, so it can be used at a lot at various examples. First, send a large read-only lookup table to all the nodes. Second, large feature vector in a machine learning algorithm. And it basically is like distributed cache of Hadoop. So broadcast variables are quite useful when you want to share a piece of data to all the nodes. And Spark tries to optimize the broadcast variables pretty much. Okay. So let's say you want to remove common words. So you can broadcast the common words to all the nodes and sc.broadcast. Okay. So you get the you got the handle to it, and using this, okay, you can always get the data. All right, you always get the data. There's nothing right now, but if I want to broadcast something like this, or maybe an object, all right. So x dot value, so you can see that the data is there. So this can be used as kind of shared variable. Although the same thing, you can basically create a local variable and share it across. I mean, the same, if you try to access a variable from a function, then that variable will automatically go with the code. All right. So you can execute the external commands. That's not too much required. Okay. Also, Spark provides you with the basic functionalities, basic few functions of statistics. Okay. So I'll just try to show you. So that's a Python code I'm converting into Scala. Okay. So this A is essentially A can give you standard deviation. You can see we were able to quickly compute a standard deviation. And so it basically provides you with these nice statistics variable, statistics functions. Okay. So that's about little bit more into the Spark RDD. So we talked about accumulators, we talked about the broadcast variables, and we talked about the statistics functions. Okay. Now let's talk about something very, very important. Let me clean it up. Good. All right, let me start. This is a very interesting topic, and I would love to show you the entire working stack. Okay, so be ready to experiment. All right, so we have already talked about the something called unbounded data set, right? When we were talking about Flume, we talked about how the continuous computing works, how the unbounded data processing works. meaning these kind of programs never stop. They keep running, right? And their lifespan is decided by data. If data is coming, it'll run. If data is not coming, it will wait. All right. So that's called streaming. That's called streaming application or processing of unbounded data set which do not have any boundaries. Okay. Example could be that let's say you are continuously displaying your brand awareness globally. Okay, so continuously you are scanning Twitter and you have put a hook that when people talk about you, your brand's name, then you essentially compute the total number of mentions and tries to put it on a graph showing to the world that whether your popularity is going down or going up. Similarly, let's say there is a process whose responsibility is to 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 continuously send the emails to all the users about their order updates. So this process will continuously run and it will wait for input data to come. And as soon as it receives input data, it will send the email and again wait for the new data to come. So such applications require a queue or a continuous data source, unbounded data source. And that those kind of data source are Kafka, Flume, HDFS, ZeroMQ, or Twitter, or maybe a port on which some process is running. Okay, so let's try to understand the, okay, so there are many frameworks which allow you to do the processing of the data lying in the queue. Okay, data lying in the queue. Queues are like enterprise buses, if you have heard about enterprise buses, whereby there are producers and consumers, and anybody can be consumer, anybody could be producer. Okay, so users put their data into the queue, it flow, and everybody else who's listening to the queue get notified. Okay, and so on. And these queues are quite powerful. So we will take you through Kafka if time allows us. All right. Now, this was about general queue processing or unbounded data processing or stream processing. Okay, let's talk about Spark specifically. So Spark streaming is a very thin layer on top of what we have read so far. So far, we have read that there is some data, we create the RDD on top of this data, and then do the processing, right? The way we have been doing so far, we have some data, we convert it into RDD, then we either break these elements in RDD into more elements, or we remove certain elements from it, or we clean it up, or change it, transform it, group it, sort it. We could do a lot of things, right, on top of RDD. That's what we have learned so far, right? So this is Spark streaming is a very thin layer on top of Spark. Okay, and what it does is it continuously reads the data from the source, and for every window, let's say whatever window you define, for every window of time, as in 1 second, 2 second, or 3 second, or 10 seconds, for every that duration, it'll keep reading the data from the input source and create an RDD out of that particular data, and then execute all the whole program which you have written on that transient RDD, the temporary RDD. So your piece of code, the map, the reduce, the filter, the sort by, order by, and all that executes on that piece of that RDD, which is temporarily created every second. Okay, so that is Spark streaming. So essentially, so Maggie's question is that what's called Lambda architecture? So Lambda architecture, I think, uh, all right. So I'll describe Lambda architecture very easily. When there is a inflow of the data, there are two things you would like to do. One, you would like to process it right away now. Other, you would like to store it and do the batch processing on top of it. Okay, so there are two kinds of uh, flow. One, input data is coming in, and you continuously running Spark streaming. That's one flow. And the other flow is the data is going into HDFS. Okay, so it looks like this. So data from source is coming to you. One form is going into HDFS, other is Spark streaming. So it looks like Lambda. Okay, it looks like Lambda. This is going into, say, HDFS. Okay, and this is going into Spark streaming. Good. So that looks like Lambda. All right. So yes, so Spark streaming is part of Lambda. We have earlier read about one leg of Lambda. Now this is another leg. Okay. So essentially, whatever data is coming in, we are breaking it into the batches. And for each batch, we are executing all the map and reduces which you have configured. And then after that, it's saving to somewhere. All right. So and sometimes, okay, sometimes you can also view it like this. So the input data that is coming in, for 0 to 1 we have created one RDD, for 1 to 2 another, and so on. So there would be many RDDs created out of the incoming data. All right, sometimes you may want to reorganize your RDDs are nothing so sorry. So when input data is coming in, it's converted into D stream. D stream is nothing but a stream of RDDs. Sometimes you may want to reorganize it, and that's called window operation. All right, so let's try to do something cool, and if time allows us. Okay, all right, so let me try to start with here. Okay, and first of all, I don't like too much of text on my screen like this one. I would like to turn it off. Okay, how do you turn it off? I'm also pasting it here, and let me convert it into like proper comments. I'm still very used to Python. Okay, so I've pasted it. I'll explain to you what each line means. First, we are turning off too much of verbosity on our console. Okay, now you will see that when I say a dot mean, it gives only this, no extra information. All right, we should have done it long back before starting the session, but okay. Now let's start the Spark streaming. We are saying we want to use the Spark streaming library. For that, we have to import a particular package. So we have imported the package. Good. Next is we are creating handle the way we have SC, which is Spark context. Similarly, we are creating a streaming handle exactly in the same way that way SC was created. We are saying SC, and we are providing one more argument. Okay, we are providing one more argument. Let's say here it's 10 seconds. So for every 10 seconds, it will accumulate the data together and create an RDD out of it. Every 10 seconds, it'll do that. Okay, so this Spark streaming context, this handle points to that temporary RDD. Okay, it points to that temporary RDD. Now let's define the input data stream. We are saying, we are telling streaming that, hey, connect to this particular host at this particular port and read the data, meaning there would be some service running at this host and at this particular port. So whatever data you get, you create an RDD out of this. This is basically D stream because it's a temporary RDD. So this lines is basically, if you take a look, is basically a D stream. It's not RDD because right now we are telling Spark streaming our steps which it will execute on every second's data. All right. So we have set up the input process. Now we are saying using flat map break the input data by space. Okay, so basically we are every second we want to count the words frequency. Okay, every second. So for every second's data, we first split it by space, then convert it to tuple, word comma one, same as what we did, and then reduce by key. Instead of saying a comma b and then arrow, this time I've tried to look a little more cooler. And okay, now let's go. Good. I'm also going to paste it here. Next is I'm going to print the results, which means this print is going to get executed every 10 seconds. All of this, all of this from here onwards, from here to here, it's going to get executed every 10 seconds. Why 10 seconds? Because this we are going to put 10. All right. Have we put 10? Or yes, we did put 10. All right, now let's try this. Okay, so we have basically set up everything. Now only thing we have to do is start. We have not started yet. We have just created the our evil plot. Okay, but we have not yet started the program. All right, because for starting the program we'll need the input source. Let's set up the input source. So what we are going to do is we are opening another tab. Okay, let me open another tab. Yes, I have connected in the another tab e.console. I'm in both the things. I'm at e.console, e.cloudxlab actually. Okay, let me, and so here on the first console, in the first console, I'm going to read data from a particular port, and in the second console I'm going to produce data. Okay, I'm going to produce data. And how do I produce data? First, I'm going to set up a dummy service called NC. NC is a quickest way to create a server. Okay, so in the another console, this is what I'm going to do. All right, so here I go. So I've started this server on 999 port. Okay, now you can actually connect to this port and write to it. Okay, and read from it. So whosoever is reading from it will get this data. Okay, whosoever reads data from this particular port, I've created a dummy server who is listening at 999 port and producing this data. Okay, now and here earlier we have told this guy, this Spark streaming, that read from 999 port. Okay, so essentially I'm going to read the data from a port, and I mean the Spark streaming is going to read the data from the port and count it. All right, so let's do the magic. So this way, in case I'm running on 999 port and you also want to run, you can do it on different port. Okay, use some other port because only one process can run. Now let's kick off our let's kick off our Spark streaming which we had planned earlier. And how do we kick off? Using SSE. Okay, let me see what error are we getting. No input registered. So I'm just trying to put something. Let's wait for 10 seconds. I think 10 seconds was a bad idea. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Was it a bad idea? I think so. I think let me just exit it, and I will try to do it once every 1 second. And I'm going to show you how we can process 1 million records in a second. Okay, and that I'm going to show you that today. Okay, I hope it's okay to go for 5 minutes, right? 5 more minutes because we are over time. All right, here we go. Sure. Okay, so I have basically set up everything. Now let me check if my server is running. Yes, it's running. And here we go. Now I'm saying SSE wait for start the computation and wait for termination. Okay, I'm saying wait start, and then I'm going to say wait for termination. Okay, good. Now see the magic. I'm going to say I'm going to type quickly and then see on the other side if it's getting printed. You see, it's counting every second whatever the data is coming in. All right, now there is something very interesting I'd like to show you. Okay, and in case you missed this part, those who are trying to do it with me, okay, so this is how I started the process. All right, now let's see a magic. There is a command called yes. Okay, for people who are highly assertive, this command is cool because it keeps on giving y. And where do we use this kind of command? In case there is an installer which is asking you to type too many y's, there are too many agreements to click on y, you can just pipe the data from yes. Now, I'm going to pipe this yes command to NC, which means there will be millions of y's going to Spark streaming every second. You see this? You see how many y's have come in a second? 3 plus 3, so 2.5 million. I'm hoping it does not freeze my whole cluster. Okay, so this is I'm generating like huge data right now, and it's going to this. I'm hoping this is running fine. Let me try to restart. Okay. Yeah, it was actually computing. You see, it was actually computing a lot. See, 7 million per second, and here it started shutting down, and you can see this. Okay, so you can see that we were able to do quite fast computing per second. Okay, oh, it was 10 seconds. Ouch, that was the reason. I get it now, why it was so bad. Okay, all right, so yes, So you can try by yourself. So this thing is actually working very well. And yeah, let me just change it. It'll look pretty cool if I do it every second. And it always looks cool when you do it every second. All right. Okay. So is anybody else trying? You want complete code? All right. Okay. So right now, nothing. Now let's see the magic. Now see the magic here. This time, okay. So it's counting Y's, number of Y's that are coming per second. The character Y. Okay. Because we are generating only Y. Good. I think somebody else has started reading from me from the same 999 port. That's why it's going empty from me. Is it? Jayaprakash? All right. So is anybody else reading from this port from me? Okay, because that's why it's going empty here. All right. Okay. So this is the way. This is the way we can do a stream processing at a very fast pace. Right now, we were able to kind of do in our best case scenario. If you see earlier, we were able to go up to 3 plus to 1.2 million records. So question from Maggie is that what do you do when you have multiple readers? Generally, the server asks for login password and you authenticate with them. Every queue has got certain authentication mechanism, and therefore, before you connect to the server, you will have to provide the login password, and hence there will not be such conflicts the way we are having right now. Because right now, for the demo purpose, we have created dummy server which does not ask for login password. So Sasi's question is, it is different each time based on load it's processing. Yes, because it's distributing it amongst the cluster and a lot of things are going on. Therefore, it is number of Ys that are being captured every second are different at different times. Okay, so I hope was okay. So Maggie's question is, so do you need to architect one port per listener? Generally, right now we are reading from a port, right? From a network port. In reality, we will be reading from a queue or any other system or a process from a file system or a continuously updating file using tailman SF. We would be reading from those kind of sources. All right. And in case if this is the circumstance, what we are seeing right now, in these cases, we generally make sure that different processes use different port. In that case, your point is correct. All right. Great. So this was our stream processing today. We will continue our discussion from Kafka. Okay. We will, I'll leave you, the Spark streaming example in Kafka to you. Okay. We have, I mean, it's exactly same what we have done today. Just that, just that the query is a little different. Okay. The connection is a little different. All right. So that's pretty much. And okay. Have a good day. See you tomorrow. All right. So see you tomorrow. We will continue our discussion on Spark SQL and one example on MLlib and GraphX. Okay. Good night. All right. Thank you, Maggie. I'm happy you liked it. All right. Thank you, Jayaprakash. Thank you, Michelle. Good night. Thank you, Dheer. I'm happy that you liked the session. Thank you, Hank. All right. So we are continuously working on CloudX Lab, and it'll be great if you also kind of subscribe to the blog or maybe Twitter account, so we keep on updating whatever we do there. Okay. And so stay connected with CloudX Lab as well. That's the point I'm trying to make. All right. Tomorrow is going to be the last class, Pankaj. All right. And be ready. Maybe we might have to extend maybe 10 minutes, and but nothing more than that. All right. Bye bye. Have a great day ahead.